Hello everyone, welcome to Practical Mechanics. I'm Mohsen. Today video we are going to talk about orientation controls in GD&T, geometric dimensioning and tolerancing. Orientation controls control the orientation of feature and feature of size with respect to datum. It means parallelism, perpendicularity, and angularity. These are orientation controls. Let's today just talk about parallelism. Parallelism can be applied to a planar surface as a feature or to a feature of size. In the case of that is applied to feature of size, it can be applied to a center plane or derived median plane as a feature of size, and also can be applied to an axis, cylindrical feature of size. And this cylindrical feature of size axis must be parallel to datum, or center plane must lie or be contained within a zone or in the zone tolerance that is parallel to a datum. Let's explain it by some simple figures. If I draw a three-body diagram, three-dimensional object, and in here we have a top and bottom surface. Here, this is the top surface, and this is the bottom surface. Then, if I have a look from front and I draw the 2D view of the front or front view of the object, which is this one, then this line represents the top surface and this line represents the bottom surface. I choose the bottom surface as a datum. Any datum sign symbol has a base, filled or unfilled, in a box which is the house for name of a datum. We called it, for example, datum A. Datum can have name from A to Z, except a few letters cannot be chosen as a name. And I wanted to specify that top surface is parallel to the bottom surface. And I know as a designer that making parallel surfaces in production process is not possible to make a perfect parallel. Then we specify a zone shape. Zone shape here for this planar surface is a space between two parallel planes. And we show them that zone shape with, let's choose another color, two parallel surfaces. For example, say this one. Because making parallel surfaces, perfect parallel surfaces, is not possible, we specify a zone, a space, and we say that if this real surface, because of many errors that happens in production process, lie within a tolerance zone, that this tolerance zone is parallel to datum bottom surface, then we specify a zone size as well, for example, 0.2. We give this allowance to the manufacturer that I know that you cannot make perfect parallel surfaces. Then I gave a zone or an allowance for your errors. And the real surface must lie within this zone tolerance. And this zone tolerance, this zone is parallel to the datum A. How I can show this one? How I can show that I mean that? I must send a message. My message sent not by letter and not by text under the drawing. I just draw it. My draw is perfect because it's drawing. And then I apply a feature control frame parallelism symbol, pointed to tolerance, datum A applied to the drawing top surface. There is no need to show the interpretation or meaning of this feature control frame on the drawing. Drawing is like that. And everything that I showed it before, zone shape, which is parallel, and zone space, which is a space between two parallel planes, and the zone size, which was pointed to, that's the interpretation of this symbol. Okay, this means that the top surface must be parallel inside the tolerance zone pointed to size to datum A. That's how parallelism applied to a feature. We must specify datum when we say that the surface is parallel. They expect we continue our sentence and say parallel to what? They are expecting we complete our sentences. The surface is parallel to datum A. Then orientation control needs datum. And this parallelism indirectly control flatness as well. Indirectly control flatness. In the lesson of flatness, I told you the flatness must be refinement of some tolerances similar to profile of a surface, orientation tolerances, position tolerances, and circular and total runout. After till 2018, ASME 14.5, 1994, 2009, there were two other tolerances, location tolerances, symmetry and actually concentricity. But in 2018, ASME 14.5, Y 14.5, 2018, these two tolerances are out, concentricity and symmetry. They are parallelism must be refinement of profile of a surface, position, total runout, and circular runout. What does mean refinement? It means that if you specify the position of this surface with respect to datum, and because position control indirectly parallelism as well, or perpendicularity or angularity. But it means that if the focus is not only the position and also parallelism or angularity or perpendicularity are important, you must specify a tolerance for perpendicularity and tolerance as well. And this tolerance, because position indirectly control orientation and you specify orientation, this tolerance for orientation normally is smaller than the tolerance for position. But refinement doesn't mean only that it must be smaller. No. Refinement means that if you specify position and also you specify parallelism, it means that you emphasize the parallelism of this surface, not only the location of that, but also its parallelism to datum A as well. For flatness, it's the same. Parallelism indirectly controls flatness of the surface because the surface must lie within a tolerance zone. And all top high points and lower points also must be within be contained in the tolerance zone. In this case, you are indirectly control flatness. But if the flatness is important here, we say that, okay, flatness tolerance must be a refinement of orientation control as well, or position tolerance, or profile of a surface, or total and circular runout. In this case, emphasis is on flatness as well, not only parallelism of the surface. Parallelism needs datum. Flatness doesn't need datum. That's the difference. But if you use parallelism and flatness applied to the same surface, both, then this flatness must be a refinement of parallelism. Here you have the flatness as well. For example, point 1. In what cases we cannot use flatness orientation or parallelism cannot control flatness? In what cases? We can use modifier for orientation. And the only modifier that you can use here for parallelism is when it applied to a planar surface is T modifier. What is T modifier? I can bring here T modifier. T modifier means tangent plane. When you use tangent plane, why we use tangent plane? Sometimes the surface is so irregular that measuring its parallelism is difficult with dial indicator. Dial indicator just we have a fin-shaped surfaces or something like that. In this case, assume that this is the real surface, and you want to check its parallelism with respect to this datum. Then what you did, you used a perfect flat surface and put it on the top of the surface, something like that. I bring it a little upper, that can contain all of them. And then you check your dial, you put your dial indicator on this top surface, which is called the tangent plane. It's a very thin, planar, perfect flat surface that you can put on the surface of the object, and then move dial indicator above that to measure it. And the zone And this tangent plane must be inside the zone. Tangent plane must be inside the zone. And some points from the surface may be outside the zone. In this case, only tangent plane is in contact with the high point of the surface. And tangent zone must be actually contained, or the tangent plane must be contained in the zone space. In this case, this parallelism tolerance cannot control flatness of the bar. Then you are allowed to use T modifier for orientation that for parallelism that apply to a planar surface. In this case, the tangent plane must lie within the tolerance zone, and flatness is not controlled by this parallelism. That's everything that we can say about the tolerance, but it depends. Sometimes how flatness can be controlled here. The question is this. You must have a look that this surface actually has the only geometric terms that apply to that is parallelism. Is it the only geometry? And it has a size tolerance as well. 10.2, 9.8. In this case, flatness controlled by size tolerance. 10.2, 9.8.4. When you have a tangent plane here. And if you have another tolerances, for example, like tolerance of a profile of a surface. Let's use profile of a surface, for example, 0.5 with respect to datum A that apply to this surface. Profile of a surface. In this case, flatness controlled by the zone 0.5, zone size is 0.5 for flatness as well. Okay. All lower point and upper point must be in a zone which is the size is 0.5. If we have a T modifier here, if we don't have T modifier, we don't have tangent plane, and this orientation parallelism also control flatness as well. That's for flat orientation that apply to a feature. Let's consider feature of size. See what happens. Feature of size, we have two feature of size here. Do not need these tolerances that apply to feature. First feature of size assume that we have a hole here that is horizontal cylindrical hole here. And if you look at to this here, you just see a circle. And you must apply the tolerance for this hole. This is the datum. I apply parallelism for the axis of the hole. And let's show the size. Phi is 4.23.85. And then orientation control underneath the size. Parallelism, phi modifier, 0.2 with respect to datum A. It means that the axis of this cylindrical hole must be contained in a zone tolerance that is parallel to datum A. What is the zone shape here? Zone shape here is a narrow cylindrical object, size 0.2. Let's show another view here, side view. If I show the side view of this object here, I have these holes as well. And axis doesn't exist. It's a series of points which we call them derived median point. It's a set of derived median point represent the axis. If this set of derived median point that represent the axis of the chart must lie within a tolerance zone, which is a narrow cylinder. Is the zone shape here for the axis. Narrow cylinder. This narrow cylinder must be parallel to datum A. I can show datum here as well. Base can be filled or unfilled. Both is accepted. Then it means that the axis of this hole or cylindrical object must be parallel to datum A with 0.2 parallelism tolerance or 0.2 parallelism error. It means that the size of this narrow cylinder is 0.2. And axis must lie within that, like this one. Assume that this is the axis. We use phi modifier for axis because the zone is cylindrical object. We can use modifier M, L, P, projected tolerance zone, it means. Later in the position tolerance, we talk about this P modifier as well. Not T and U. We do not use them, not T and U. For M and L, you know them. MMC conditions and LMC conditions. You know the actually MMC and LMC. P is projected tolerance zone. It means that the zone is projected outside of the object. And we have a projected zone height as well that must be mentioned here. If I put P modifier here, later I explain it when we reach to P modifier here, 10. It means that the axis of this hole not only must be within this narrow cylinder, but if we extend this narrow cylinder outside, how much? 10 millimeter, and I extend the axis must still be inside this zone because this is required for assembly. That's the meaning of projected tolerance zone is used. Not only axis must be in the zone inside the object, but also if I extend the axis, for example, 10 millimeter outside, and extend the zone as well 10 millimeter, and I extend the axis must lie in this zone. This is called projected tolerance zone. And this, how much is outside, depends on this number that is written here. You can have, besides P modifier, you can have M modifier as well, or L modifier here as well. And We cannot use T modifier here. Why? Because that's our axis. Tangent plane has no meaning here. And also for another feature of size, which we called it, before I raise it to go to the center plane and apply orientation tolerance to center plane, I must explain the M and L. You know M and L, send 3 messages to manufacturer, rule number 1 does not apply. Tolerance at MMC size is exactly this amount that is mentioned here in the feature control frame. And also bonus tolerance is permitted. And zone shape is the same narrow cylinder for axis. And zone size is variable because you have an M or L modifier that at MMC we have 0.2, or with L modifier at LMC we have 0.2. For the other sizes that departs from MMC or LMC, total geometric tolerance is increases. And in this case, the size of the tolerance zone also increases and is variable. You know that for flatness and for straightness, we talk about it and we construct the table and we show it at how to calculate bonus tolerance. You can return back to that video about straightness and flatness with M or L modifier. Let's consider again another feature of size here. Assume that we have a width here, slot, internal feature. If we have an internal feature, for example, then if we get the size of this feature, for example, 4.83, 4.8, 4.6, and then apply parallelism tolerance here. No phi modifier here, 0.1 with respect to datum A. What does it mean? It means that center plane, which is derived median plane, doesn't exist. It's only a set of points. Okay, derived median points that represent this surface. Must lie within a tolerance zone that tolerance zone is parallel to datum A, the bottom surface. That's datum A, bottom surface. Then zone shape must be parallel. It means two parallel planes. They are 0.1 apart. 0.1 mm apart. That's the size of the tolerance zone. We call it zone size. Then zone shape here is the space between two parallel planes that contain the center plane or sets of points. We can show it like that. We have a two parallel plane and the real surface, which is the center line, which is a set of points, lies between them. Lies between these two parallel surfaces. And this space between these two parallel surfaces is zone space for this tolerance. And their distance here is 0.1 mm. Zone size. Then, orientation can be applied to a planar surface or can be applied to a feature of size. When we use orientation apply to here means parallelism. Applied to a planar surface, it can have T modifier. When it applied to a feature of size, it can have, it depends. If it is an axis, L, M, P modifier. Now T and U modifier. And phi modifier as well, I must add them. Phi, we use it because it's a cylindrical zone shape for axis. That's the important things about the orientation. We can talk about it hours and hours, but that's the summary and important and brief information about the parallelism tolerance. Thank you for watching. See you in the other videos for perpendicularity and angularity.